Well, good afternoon to the second day of our desalination talk for the Action for Water program. For those who were actually following the first talk we had on Monday, my name is Luewton Agostinho. You don't have actually to in the Netherlands. We are not very used to the titles, so you can just call me Luewton if you want, or Agostinho. Today, in the second talk, we are talking about a little bit more, because we already started the last time with the thermal desalination systems. I abbreviated as TD there in the title. I will talk a little bit more about the seawater reverse osmosis, and then we will finish this talk discussing about the brine management and some environmental aspects. So if you have any questions or if you have any comments during the presentation, you can actually just stop me, or you can you can make the questions, because we have the system in a loud microphone here, a loudspeaker here, so I will be able to hear you. Maybe you can quickly also test your microphone. Some of you can say something to see if the volume is loud enough, so I would hear if you have some questions and I can stop. I just checked with Sebastian, but I made a small change here. Can you, Sebastian, maybe you can say something again so I can see how the volume is?
Say again, please. Sorry, you can repeat for me?
Oh yeah. No, it's just to check my own speaker, but it's okay.
Mm-hmm.
Okay. So let's start. It's important to say that this is an introductory talk. So last week we had 1.5 hours, 2 hours, and today we'll have also 2 hours. And desalination is really huge, it's really big. So ideally, you will see this as an introduction to many different parts of desalination. It's not an in-depth class. This is a module that takes me at least 40 to 60 hours, which is now condensed in 3.5, 4 hours. So the different aspects we're going to be talking, they will be superficially discussed. And if you would like, of course, and you have more questions, you can approach us per email. Additionally, we discussed the last time with the organization of the program that I will prepare a folder with the different papers and presentations that we used, so you can access the information as well. Most of the information which is presented here in forms of papers or other types of reports. So okay, let's start. The talk now, as I mentioned earlier, it will be about the thermal process, MED. Especially we talk about MED and MSF, because they are the biggest ones right now in the market. The SWRO system, so seawater reverse osmosis, and we talk a little bit about the brine management part. So I think you remember this slide from the previous talk, that basically in desalination now, let me see how okay, it's right. In desalination now, we can find many different types of processes. But mostly we can divide them in membrane available in the market, especially for municipal water treatment. We have basically the thermal process and membrane process, especially reverse osmosis, and these two first processes that are dominating the market. So in this talk we will specifically cover in thermal process to give you an idea of functioning, how the MSF and the MED processes works. So this is just to give you an idea about how big these systems can be. So this is a MSF multi-stage flash desalination plant in Saudi Arabia. So maybe you can see from this picture here, there's a tractor there and a person inside. So you can have an idea of magnitude of how big these systems can be. So the system produces 470,000 tons per day of water in Saudi Arabia. But if you would look, what would be flash? What would be this MSF? What would be this flash evaporation? So just to bring you a bit of the theory back, I think you have all seen this phase diagram when you study thermodynamics in high school. And the phase diagram is basically to show you at which pressure and temperature levels you will have different states of a specific substance. In this case, water, for example. So you will see that at a certain high temperatures and low pressure, if you have low pressure, high temperatures, yeah, your substance will be in the vapor phase. If you keep the temperature and then you increase the pressure, again, pressure is in Y and temperature is the x-axis. So if you increase pressure, then you move to a liquid phase. And in the case of keeping the pressure and decreasing the temperature, you can move to the solid phase. So solid phase is low, well, it's low temperature at a variety range of pressures. You can still have solid phase. Vapor, you can have at high temperatures and relatively low pressures. And if you increase the pressure, you can move to the liquid phase. So if you think about the flashing zone is exactly the way of evaporating your liquid by means of manipulating the pressure. So what you can do is that you decrease the total amount of thermal energy that you need to evaporate. In the case of flash, is actually the flash is also related to how fast you do this, because when you do this change in pressure very fast, you can also increase your total evaporation rate. So the flash zone will be around the zone where you have the liquid vapor phase, especially at low pressure zone. So, and how can you translate this to a desalination? Oh yeah, again, so you can see that this is also an interesting plot. You can see that the flash evaporation zone, which is the zone 2, it's both a zone where you decrease your total pressure, but also you decrease your total temperature, meaning that you can keep your evaporation at low temperatures. And in the industry, if you want to use evaporation as a main process to remove your salts from your water, yeah, doing this at low temperatures is always an interesting option. A typical MSF system works more or less like this. You have a completely closed chamber, and then you put your brine in. In this chamber, of course, you can manipulate your pressure, so you decrease the pressure inside. So with a control valve, as soon as your brine enters, as soon as your seawater enters, then the pressure will be the environment will be suddenly at low pressure, and then you have the flash evaporation. The flash evaporation generates the vapor. You use the misters, so just to avoid that droplets will be passing to your condensation chamber. Then the vapor passes, and then you have a tube bundle at low temperature that will condense your water, and then you will collect your distillate out. So it's a very simple, it's a simple concept, even though it requires a lot of pressure and temperature combined control. But of course, in a MSF system, what you want to do is that you want to do this in stages. Because you can use the temperature of one stage to actually improve your energy efficiency of the whole process by transferring this energy to the next stage. So this whole process that you have just seen is actually a continuous process when your feed is moving from one stage to the other. And what you will see is that as soon as you condense, you're gonna have some heat exchange, and then you can use also your heat from one, you can use your heat from one system to the other. So the flow of your feed is counter flow of your seawater bundle, of your, let's say, cooling parts bundle flow. This system also have a very important, let's say, non-condensable gases steam or ejector control, because to keep this pressure, you want to avoid gases that the gases are accumulating in your chamber. So as I said, this evaporation happens at a very specific pressure. So the moment that you start to evaporate in in a flash chamber, you will condense some vapor, but of course there will be no condensable gases. So if you don't exhaust these condensable gases, you can build up pressure inside your chamber, and then you can move in this phase diagram position to another position which will decrease both your flashing chamber efficiency, but it could also at the end compromise your condenser efficiency. You have to remember that the phase diagram both dictates pressure and temperature for evaporation, but also for condensation. So we want to keep a pressure and temperature control in the evaporation part of the system and the condensation part of the system. And if you remember the phase diagram for condensation, you actually would like to have higher pressures. And for the flash chamber, you would like to keep low pressures. So these chambers have to be separated. And well, this is just to show you a little bit bigger image of how the systems would be. So that's the fact that these thermal desalination systems are done in stages. It's basically also the reason for them to be called M. So MED, MSF, because they are multi-stage. So they are multi-step systems where you can use the heat from one stage to the other. So in this case, I'm just multiplying the stage here. As you can see, that at the last point you will always have a brine blow down. You always have a brine, let's say left feed. Why? Because we discussed the last time, in desalination, you don't want to move to very, very high concentrations in your brine. You want to keep it to a certain percentage to avoid high concentrations would cause eventually saturation of the salt, and which will cause eventually deposition or scaling in your two bundles, and it will or stop the operation or even generate very costly maintenance steps or maintenance actions. Well, you can in here you have also the steam generator. For the steam injector, you can also use for the high pressure in the condenser zone. You can see also that the recirculation of the brine recirculation pump can be used to re-inject the condenser, the liquid in the condenser phase. And sometimes, as you can see here, you have to divide depending on the amount of the stage that you have. You have a temperature control, and then at a certain plateau temperature level, you have maybe to divide your feed in a second time. So,
Can I ask a question?
Yeah.
On the previous slide.
Mm-hmm.
At the bottom right, it says there is a distillate pump and potabilization. What does that do?
Oh yeah. Well, normally in this good question. Normally in desalination processes, especially thermal processes, also by the way, reverse osmosis, you reach a very high purity level. So because when you distillate and you condensate, you basically just get clean water, distilled water. And distilled water cannot be distributed. It has to be a minimum conductivity. It has to be a minimum amount of salt of it. So the potabilization here means that after you collect all the water distillated in the condensation chambers, you have to pass through a post-treatment process. Normally a remineralization step where you're gonna re-add the salts. So it's a little bit controversial, or to say the least, that you are removing salts and then re-adding them at the end. But that's how the thermal desalination systems they work. If you want to, in a more, let's say, drawing aspect of these chambers, you can see how big they can be. Yeah. So let me see if we can identify some of the parts. So here is the exhaustion for the non-condensable gases. You can see you have the distillate trays. So the vapor is moving that way for the distillate trays and for the two bundles. Yeah, here is the big the mixture we talked about it. So the mixture actually also divides your flashing chamber, which is low here, to your distillate chamber. Huh? Well, there is a exhaust for the recycling brine, so you can remove, you can recirculate to the condenser levels at the beginning. Well, a more technical view. If you want to have a little bit more idea of, it's a little bit, the quality of the image is not very good, but I think you can see very well how big these chambers can be. This is a flash chamber of an MSF system, and this is how big a two-bundle also looks like. And the very important thing I would like, especially in this photo, I'd like to bring your attention is like, I mean, the condensing is a surface area dependent type of process. So the more surface area you have, the more you can generate of condensed water. So you see these two bundles can be quite packed and the tubes can be quite close to each other. So yeah, because if everything works as it should, the water has just to pass through them and then be collected at the lower part. However, this is a risk as well, because if you don't have a good functioning of the system, and for example, your concentration is too high, you can start depositing salts in the tube surfaces, the scaling, what we call, and then you can clog everything. So here is also an internal part. So you see, here is the demister. Here is the passing from the chamber, the flashing chamber to the two bundle part of the same plant. Well, some process constraints, so scaling control, because hot brines easily reach saturation with an organic species. We discussed about that last time. Salt water has in its composition, the majority of the salts is sodium chloride, but you have a very large fraction of calcium, magnesium, and also the sulfate part. So these are mainly the cause of scaling in these desalination plants. And the scaling restricted flow path, that's what we said in the tube bundle. So if you start to grow salts on the top, on the surface of the pipes, you can restrict the flow path and then compromise your not only heat transfer, but actually you can compromise the whole flow of your condensate. And this is about MSF. Maybe the next technology we can talk about it, which is also quite known in the market, is the MED. The MED stands for multi-effect distillation. It's a little bit different concept from MSF, but in terms of sizes, I don't know if we have. Yeah, I think these are two versions there. So in terms of sizes, you can see how big the systems also can be. This is an IDE plant in India, which produces 134,000 of cubic meters per day. And if you look in one single stage, if you would like to look how the MED system works, well, the MED, it happens, the pressure and temperature control is also important. However, it's not dependent on a flashing operation. It's actually depending on surface condensation. So what you have is that you will have your seawater will be put it in your system in a shower. So the shower, the top showers or the atomizers will actually generate the necessary surface area so you can evaporate. Then what happens is that the shower will be heating a two bundle process where you're gonna have your hot vapor passing inside. So as soon as you shower, the internal water vapor inside will condense, and then you will get the condensation. You get your condensation as pure water. Where this vapor that passes inside the two bundles, they come from? Well, they come from the evaporation in the lowest stage of the collected brine. So the fraction which is not used and evaporated here for the formation of the brine, it deposits and then creates a new vapor, which will be redirected to the next two bundle condensation step, and will form your eventual distillate. So we understand that in MSF maybe I go a little bit back, in MSF, in MSF, your distillate is outside the tube bundle, so you evaporate in the surface of the tube bundle, and you collect the distillate, while in MED, your distillate is actually inside your tube bundle. So the distillate will be condensed inside the tube. So you don't condense at the surface, you condense in the internal part of your tubes. So it's important to say, again, I repeat myself, it's possible to manipulate pressure for improved evaporation and for improved condensation. So normally the MED processes, because you want to improve your condensation, they have a vapor compression phase. So you try to actually increase your pressure. So again, temperature pressure. You try to increase your pressure at a certain operation temperature, which ranges here, depending on the plant, but in the range of 60 to 80 degrees. So you want to increase your pressure to actually condense your vapor. And this mechanical vapor compression is actually, of course, has to happen in a different chamber because the pressure for the evaporation should be low and for the condensation high. So just to give you an idea, so this will be the spray as a simple scheme. This will be the spray where you're going to have the produced gases, and then you're going to have your vapor compressor to generate high pressures in the second chamber, so you can generate your product outlet. Then, if you look this into a big scheme, you look at this into a big scheme. Well, the system works also in multiple effects, as we discussed. The M from the MED is multi-effect distillation. What you do, let's try to find your feed. So here's your feed, your seawater. So you're gonna pass to some strains and some pre-treatment, of course, to remove most suspended materials, and then all the feed will be injected in the shower, as I said, in each stage. So the showers will be showering on top of the tube bundle. And in this tube bundle, you're going to have your evaporated phase. So this evaporated part of your feed will be collected to pass to the next tube bundle. I think you can see here. So a fraction of this showered water which evaporates passes through a demister. So this is also a demister, and it will be injected in the second condenser. Which will be then showered by the second shower. It will be condensed, and then all the outlet of the condensers are going to a collection line, and then this collection line will give you your final treated water, which again have to be remineralized. So you have to add the minerals again. Here you have the thermal compressor as well. So as you can see inside, they are connected to the thermal compressor, are connected to the tube bundles, because to improve your condensation inside the tube bundles, inside the tubes, what you have to do, then you have to increase your pressure. You have ejectors and pressure recovery pumps as well to guarantee the let's say what we call it, the wet ratio in your tubes, and to avoid, for example, dry spots, meaning basically to guarantee that you have the same flow in all the points, in all the tube bundles, and to overcome the losses that you will have due to pipe length or to other types of valves or systems that will decrease the pressure, for example, from the shower number 1 and number 2. So the ejectors are mainly used to keep your wet ratio or to keep your pressure control. As I said, when you shower on top of the tube bundles, what you want is that you want to keep a certain wet or a certain feel around the tubes. They cannot be very dry, they cannot be too dry, but also they cannot be too wet. So this relation between the amount of seawater that you flow in the tube bundles and the total number of tube bundles have to be carefully controlled, because if it is too much, so if you create a too large film, then you will decrease the evaporation rate, and you also increase the resistance inside and also decrease the condensation inside. But if it is too dry, so if you keep it too thin films and you have dry spots, then these dry spots will generate salt accumulation, and eventually it will generate scaling on the tubes. So the scale formation in MEP hinders heat transfer process, increases specific energy consumption, reduces production capacity, creates capital operating and maintenance costs due to allowance for scale formation, scale prevention methods. So if you don't do it, of course, you will have maintenance costs. So via scale formation and efficiency decrease. And to avoid your process, you use cleaning and products and chemicals, so anti-scaling, for example, to control this scaling anyway. And this is basically the chemical costs that you see in thermal desalination processes. I don't know if you remember the last time we discussed about OPEX and CAPEX costing in membrane systems and thermal systems. And the thermal systems, they do have a chemical cost, but smaller than the membrane cost because of the SIP. But these chemicals are mainly, I repeat myself, to control scaling, but also anti-foaming, because foam formation, especially due to the showers and large surfaces, they could also decrease drastically your efficiency or create contamination passing through the limits. Is on the outside of the tube, so prevents the mechanical cleaning methods such as ball cleaning system. I mean, you saw how packed these tubes they are. Once you block them with salt, well, cleaning is almost impossible. You cannot do it. You have to remove. So again, to avoid this, you have to keep a good wetting rate, and then there are numbers that you have to calculate. You have your wetting rate. This was a course done by in Genoa, where he was very specific about the types of numbers that you have to consider when you dimension this type of plants. Also, if you want to see well the interior of such plants, so it's more or less the same what we have seen in MSF. So the chambers are very nicely separated. You have an emitter basically separating the two parts. In this case, you have your brine pool down there, and here you have your two bundle for the showers. So the showers are on top of it. You have a two bundle, and here the condensate vapor will be collected as a distillate, and you have your produced water for a post-treatment phase. For a post-treatment phase. Okay. The third type of process that we would like to talk about it is the seawater reverse osmosis. Then this is also just for you to have an idea of magnitude. This is also a seawater reverse osmosis plant done by Suez and Emirates Arabic, producing 36,000 cubic meters per day. The main principle of the seawater part is that it's a membrane system. So membrane systems, you have to think in a very simple way. A membrane is like a cloth. So if you look very close to your cloth on a microscope, you will see that it's not completely closed. You have fibers, and then in between the fibers you have spaces. So porous. So imagine that you want to use the clothes and you want to put some water on it. Everything which is suspended in your water, which is bigger than the spaces, will be retained, and everything which is smaller passes. So when you want to use membrane systems to remove salts from water, then you have to have porousness that are smaller than your salt atom ratio. And these are normally the reverse osmosis membranes. So they could go, the porousness could go as small as 0 nanometers, which will be enough to remove your salt. So, but of course, the smaller the pores they are. So you see also with your t-shirt, if I put water here, it will pass because the pores are quite big. But if I get a membrane and with very small pores and I put water in it, it will simply not pass. So the smaller the pores they are, the more pressure you need. So reverse osmosis or maintenance systems require quite high pressure. So main advantages are the low energy consumption is actually there for the thermal energy, because the reverse osmosis don't use thermal energy. Well, compared to, you saw also the capex cost, the capex related to thermal processes are relatively low. You can use mechanical electro energy only, so you don't need the thermal energy. The plants are quite modular, so you can increase or you can well play with demands per year. And the environmental impact, well, depends on where you consider. So, but it is, for example, in the thermal aspect, so the temperature of the brine is indeed lower than for thermal processes. But I mean, in salt concentration, it will be the same. And of course, also reverse osmosis systems, they also use chemicals for the seed dust, for the cleaning of the membranes, which will be eventually part of the brine. Clear feed, need for pre-treatment, skilled staff. Well, the systems are becoming quite, let's say, popular now. So more and more technical operation staff is coming, level technical operation staff is coming. And energy consumption is affected by salt concentration because, of course, the higher the salt concentration, the more the pressure that you apply. So this is just a very simple idea of how I was explaining with my clothes, but how the membrane systems they work. So as you can see, there is a certain water flow that depends on a delta P, on a pressure, on a basic pressure difference between the beginning of your membrane and the interior of your membrane. And this is related to your conductivity, which is represented here by your JS, the salt volumetric flux. So the conductivity, the more the conductivity, the more is the deposition on your membrane, and the more the pressure that you have to use, which makes a little bit a different energy demand compared to energy calculation compared to thermal system. So a typical seawater desalination process can be presented like this. I mean, as you could see, the advantages and disadvantages. You have to make some pre-treatment to avoid accumulation, biofouling, or any kind of scaling in membranes. So there are many different ways. You can also do with other types of membranes, for example, with filtration. But the first plants, I would say plants constructed 10 years ago, in between 10 and 15 years ago, the most used system was a coagulation followed by a multimedia or cartridge filter. So there is a necessity of pre-treatment, which is not that specialized in thermal systems. You, of course, as I said, because the membranes are quite small, you need to have a high pressure pump. And this high pressure pump is necessary to generate the necessary flux. But most of the systems, what you do, because even the outlet pressure is still higher than what you would normally need for the distribution. So what you can do is that you can use boosters pumps, or you can use pressure exchanger to recover some energy. So there is an energy recovery step as well, or a fraction of the system, which is quite normal in this type of processes. And as well as in thermal desalination, the membranes also produce quite pure systems, quite pure outlets. So you need to remineralize. So there is a necessity to add minerals back, and this can be done via contact chamber, an exchange contact chamber. And depending on where you are, even after the second addition of minerals, you still have to you still need to have a disinfection step. It's not represented here. Not disinfection, but chlorine adding aspect, because in some countries, for example, in Brazil, in most South American countries, you need to have a chlorine residual in the network, and then you also will get quite low levels of chlorine. So after adding minerals, you have to have a chlorine addition system to guarantee a minimum residual of chlorine in your network. Pre-treatments, let me see where I am regarding time, because more or less halfway I want to stop for a few minutes. Where the seawater reverse osmosis pre-treatments, the thermal processes, the added chemicals to the feed water are mainly to antifouling and scaling antifoaming, as I said. But in reverse osmosis, the pre-treatment is a critical part. I would say it's critical for both. It's critical for both, but for reverse osmosis, it has a different type of conditions or requirements, because it's basically to keep your membranes working for as long as possible. And for example, in the thermal processes are more robust indeed, but so they can handle higher levels of concentration. So the quantity of chemicals are normally per cubic meter of feed is less. But I mean, in critical aspects, they are critical for both. So you have to control the quality of your feed for both systems. For pre-treatment, you can divide it in two groups. So the conventional is the one that I just mentioned. So mechanical filtration, screening, and coagulation. But in more recent systems, you're actually using other types of membranes, like the filtration membranes or steps of membranes to guarantee the quality for your feed. The pre-treatments of the reverse osmosis influence dramatically the investments in operational cost. I think you remember that I bring the plot again, because if you can see in reverse osmosis plants, that will be here, you will see that 11% of the cost is done to chemical, while in thermal process you only have 4%. So it's important to say that I would not use critical, as I reported from the slide before. It's critical for both, but the amount of chemicals per cubic meter of feed changes in both systems, because there is higher requirements for reverse osmosis, and this is then being reflected very clearly on the OpEx costs that you have, on the higher OpEx costs for chemicals that you have in these systems. Now we go to the second part, which is brine management. So thank you very much. Let's continue the second part of the talk, which is the brine management part. There are some specific challenges in the brine management, but maybe I should start with this plot. I should start with this plot, which is a global water intelligence plot about the capacity and current production of desalination in the planet. And you can see that we are now in a capacity of 1 million of cubic meters per day. If we add we are here at the 24 more or less, so in the millions of cubic meters per day. If we add all the desalination plants capacity, then of course you have to remember that normally to avoid scaling and deposition, that normally 50% of this production is brine. So if you are in millions, in something like 6-8 millions of cubic meters per day, then we are also in the range of 3 to 4 millions of brine productions per day. So brine management is necessary because brine is a wastewater produced during desalination and hyper saline water, so salinity above 50%. The total global brine production estimated to be 51.7 billion cubic meters per year, and around 38% of which originates from reverse osmosis. Right now, because of course this is the approximated reverse osmosis share, but actually the reverse osmosis share is higher than that right now, so it surpasses the 50%. But as we also saw in the first talk, the magnitude of the reverse osmosis plants are considerably smaller than the thermal desalination plants. Brine disposal management lacks viable options. It has different options, but imposes major problems. We go through the different options, and then it accounts for 5 to 32% of economic costs, possible environmental impact, and there is currently no legislation push. So officially, there is no legislation push which obliges the companies to actually do something in the brine. The most used solution is actually back discharge. So just to give you some idea about what type of oh, I hear some noise. Somebody said something. Somebody's asking something. No, okay. Just to give you some options, there are a lot of literature. There is a lot of literature now that you can reach on brine management. So, for example, the brine management in the desalination industry by Mahokandi et al. It shows a nice diagram of possible solutions. You of course have sea disposal, land disposal. We have evaporation ponds. We will talk about them, and you have what we call it also zero liquid discharge. This zero liquid discharge. Well, it is a very broad term. I would rather, instead of calling zero liquid discharge, I would maybe call it a brine treatment with maybe selective removal. But we will talk about that as well. So you have well injection, and you also have seaboard systems injection. Well, as an option. Okay. When we look more into the technology part, so you can reduce, you can recover, you can reduce your brine with a different type of eyes, not on options, but on the purpose of this brine management. For reduction, you have the wind intensified evaporation. I will show some. These are really a technology. I will show some slides about it. We have evaporators, concentrators, which are also quite simple. Basically, the same principle of what we call it in wastewater treatments, the lagoons, the treatment lagoons. We have crystallization systems. We have membrane distillation. Two-stage are also you can play with your membrane systems to selectively separate some ions. In the recovery part, you have the membrane crystallization distillation, where you can also selectively separate. You have sequential extraction. Well, ED can be used for that. Bipolar membranes can use for that. Metal recovery. In Wetsus here, we have, for example, in the sequential extraction, we also have experience with supercritical desalination. I mean, there are different ways to selectively remove salts. And in the reuse part, we have agriculture, we have aquaculture, and we have also wetland regeneration. It's important to say that normally you can combine these guys with especially these guys. So you can, for example, combine an evaporation pond to reduce your total volume. Liquid volume with, for example, aquaculture by creating a specific species in your ponds. So when we talk about brine discharge, directly dispose of the brine in the sea environment, it's important to say that discharge is by pipe far into the sea should be enough distance between intake and outlet to minimize feedwater deterioration. Pipe should be sufficiently far out into the sea. The limitation is the cost, of course. So you have to do some studies about currents and about minimum distances to be able to define your discharge point. It's normally direct discharge at the coastal line is normally not viable, as brine disposal directly to the shore can intensify saline intrusion and can drastically deteriorate feedwater quality. It can be considered for small plants. So this relation of discharge is also discharge in coastal zone on a large deep sea is depending on the total discharge volume. Main advantage discharge at power station is high dilution, but it could be also used for thermal desalination plants because it will then, because of the large volumes of these plants, it will not impact the efficiency. To a plant for salt production, okay, environmental and economical option when it's possible. However, we will see for evaporation ponds or for salt production, one of the main challenges is indeed the purity. So which type of application you need, because you never get one single type of salt. It's a blend of different salts, and on top of that, as we discussed, there are also the chemicals for RO or for MED or for thermal processes. You also have anti-scalings, you have also antifoamings, the chemicals that could also influence the final quality of the produced salt. So just to give you some idea of thermal difference of this brine discharge when you consider the two methods that we are discussing now, the thermal methods and the membrane methods. For example, the increased salinity for thermal methods, it's rather lower than for reverse osmosis. Increased temperature also is an impact which is faced by the thermal distillation, desalination, and reverse osmosis does not have that. Reverse osmosis happens at ambient temperature. For the chlorination against biofouling in thermal process, there is biocides used. And for reverse osmosis, you have actually sodium bisulfate to remove chlorine before the membranes. However, it's important to say as well that we are talking chlorination against biofouling, so the disinfectants that has to be applied before the system itself, and there is, as I discussed, depending on the case and the country, there is a necessity to have post-chlorination, but that will not impact your brine quality. That will be necessary only for the distribution of volumes. Antiscalants, you have to keep lower pH, so you want antiscalants could be phosphonates, polyacrylic or polyamide acid, and this will be also eventually directed to your brine. Antifoams, thermal systems use reverse osmosis don't. Corrosion residuals, normally copper and nickel comes from the thermal desalination processes, which is not a problem for reverse osmosis. Coagulants known for reverse osmosis, yes. If you have a deodorant feeling, you can remove it, and cleaning residues as well. Mainly for the reverse osmosis are pH correctors, detergents, and disinfectants. If you want to get more information about overall impact of the brine discharge in aquatic environment, there are also many different types of literatures about it. So this, for example, is an example of Sola et al. That have actually investigated the decrease of species over time in the vicinity of a desalination plant. So there are indications of impacts in sea life. If we go more specifically about the solutions, for example, when we talk about evaporation ponds, you have here a big example of how big these ponds they can be for salt recovery. It's important to show more or less as well a diagram on how we have been exploring these different salts throughout the years. So before crisis, we were already getting salt out of the sea in evaporation ponds, but along the years we have been trying different approaches. Even to, I think I discussed the last time with you the concept of sea mining, where we have done some calculations in the 80s, so for the composition of precious metals, for example, it generated some kind of competition to extract precious metals. But I mean, depending on the question is, if you do this for the metal, it doesn't justify economically. If you could do this as a part of a necessity to treat your brine, it might be interesting. So other processes have been also studied for magnesium, for bromine, for uranium, lithium. So there are different. If you find in the literature different types of approach for the recovery of different brines. And what kind of salts can be very valuable? It's not very mining recovery, but can be valuable as let's say a selling product. So there are many. So as you can see in the table, calcium carbonate it's very important for the paper industry. Calcium chloride is also for cement or concrete stabilizers. Soda, gypsum, magnesium hydroxide can be used for animal feed, but also there are some studies now recently done on the use of magnesium tureen to justify the reinjection of this brine in wastewater systems. So you could improve the quality of, for example, of the nutrients in your sludge treatment for agricultural use, and so on and so forth. There are many. The evaporation ponds specifically are simply open ponds where you dispose your brine, and by evaporation you can get rid of your liquid fraction and then recover the salts later on. Mainly, it is based on crystallization of sodium chloride. Well, it's done in crystallization beds or in bottoms. Smaller ponds, it's better to avoid, for example, management, simple questions of management in large ponds or recovery of these salts. So smaller ponds connected to each other are normally preferred. And it's competitive for relatively small plants because it could generate a high quality product. However, as I said, depending on the size of the plant, the chemicals you use to clean to avoid fouling, and the quality will decrease drastically the quality of the final salt. You can do synergies, as I said, so you can have this brine disposed in the pond for the recovery of the salts, but you can also use this to aquaculture, so to have shrimps production, algae production, or you can also use for salinity gradient solid ponds. There are systems that actually are looking into this high salinity gradient sources for energy production. There are also interesting systems that I have explored, actually enhanced evaporation and enhanced extraction of these salts. And a very interesting example is the wind-aided intensified evaporation, so the wave systems. And basically what they do, they simply have a percolation wall where they flow the brine in various thin fields to a wall, and via the action of the wind, you have enhanced evaporation and crystallization, which can be formally recovered, and then you can have large production of salts for the total amount of area in much more compact system than what you would get, for example, in legumes. So when we talk about sea mining, then you have, we discussed the last time about if we can make money out of the components of this brine, of the minerals in the brine, what would be the options and how could we do this? This is more or less the principle of the sea mining. So you have to understand that again, you can find in the literature very, very different types of techniques that can be used to recover. For example, reverse electrodialysis, you can actually use, this is a technique very, very explored here at Wessus. There are many different systems, real scale systems that are already using this salt gradients to produce energy. So for example, the red stack system. You can also, for example, use electrodialysis for selective ion exchange and recover lithium. You can use the same principle actually to have production of acid and base, what we call the water batteries. That is also a system explored by us. Well, and then you have rubidium, uranium. You have the magnesium-based oxides that you can recover. So many different types of systems for many different types of applications have been already explored. Some of them, not most of them, but a good part of them already in large scale, which is the case in real scale, which is the case of red stack. But if you look to the literature, you see that a large fraction is still in bench scale, still in small scale. And that's also why, basically because, as I said in the very beginning, the ideas are there, the possibilities are there, but the plants, the companies are not yet obliged to apply any kind of brine treatment. So there is no commercial or legislation push, which is decelerating the implementation of these technologies in the market. Of course, you can play with, as I said, if you are, especially if you are doing membrane-based treatment, right? If you are using reverse osmosis, you already have a membrane stack. You can play with your membranes. You have selective removal. For example, one of the most explored cases, they use nanofiltration after the brine, because nanofiltration is very efficient in calcium and magnesium and sulfate removal, meaning nanofiltration is very good on separating or on filtering these metals, and conversely, it lets the sodium chloride pass. So if you think about NF as a possible filtering system in brine, it basically is a system that separates you bivalent ions, so the magnesium and the calcium, from your monovalent ions. So for example, you can have a feed which is a treated feed which is rich in sodium chloride and very poor in calcium and magnesium. While the brine, also the concentrate of the NF will be the opposite. So very rich in calcium, magnesium, and very poor in sodium chloride. We will see later on. I will show some examples to you that this is a nice idea. For example, when you think about using your brine to feed an electrochlorination system or electrooxidation system, because these minerals, these salts, are really need to be really avoided in these systems. They cause scaling, while what you want is really to produce chlorine-based or sodium-based compounds. You can also you also have seeded precipitation and recycle RO that you can do for different stages, precipitate different metals. You have also homogeneous precipitation, similar to what we discussed here with the supercritical systems. You can combine with membrane distillation with capacity deionization. Capacity deionization is also CAPEX is also very interesting on selective separation. However, capacity deionization also is has a certain concentration limit. So that very high concentration decreases the efficiency of the system. And of course, you have humidification and dehumidification processes, which is also which can be also fine-tuned for recoveries. So I would like to finalize the brine part with an example. Well, what we have been doing is we have been contacted by the state of Ceará, the company that treats the water. The state of Ceará has recently, in Brazil, has recently decided to build a desalination plant, and we have been contacted to, together with them, explore some possibilities for brine treatment. So the initial plan of the plant is actually sea disposal. So it's discharge, is a deep sea discharge. That's how the plant is built, but the company wants to explore systems for a near future to have brine treatment. And one of the ideas, so this is a design of what the plant will be, more or less. It's a big consortium with different companies, local companies like Marquis and European companies, international companies like Abengoa and IDE. And the plant is basically intake, a seed intake, pre-treatment, the reverse osmosis system, followed by post-chlorination, post-treatment with a chlorination. As I said, in Brazil, you need to maintain some chlorine residual. So you have also the booster and the pressure recovery system. The SIP, so for the membrane treatment, and then you have your brine discharge, which is in fraction plant. The plant is not built yet, by the way, so it's now in discussions for different types of authorizations in the city. But the idea is that you have a 55% fraction discharge of the brine mass base compared to the amount of system of the water that you will put in your system. So the first point that we discussed with the company, because they need this chlorination step to guarantee the residual chloride level. They said, oh, and what are the possibilities to actually use the brine as a source to produce our plant chlorine? So we could actually get the brine, the source of sodium chloride in the brine, using electrochemical systems, and then we can do the chloralkali systems to reinject in the plant itself. Well, as I said, the problem is for the electrochlorination system here, you want to avoid specific metals, especially calcium and magnesium. So between the quality of the brine and what you need to have in your electrochemical system, you have to make a step, you have to make a treatment. And the solution we explored, it was the addition of another filtration step where you can separate your bivalent ions from your monovalent ions. So your monovalent ions will pass, then it will feed your electrochlorination system, and your bivalent ions will be actually in your NF brine. So the idea was a first investigation of to which point the current NF membranes would be enough to give us the electrochemical quality needed for the current commercial electrochlorination systems. Is this a new idea? No, you can also see in the literature the work of Mohammed et al. That the system has been studied in different ways, and you can see also they have the same idea. So they also use nanofiltration followed by heat. So it's not something that is not explored. However, there is no commercial application of this yet. Scientifically, yes, explored. Commercially, not yet explored. Just to give you an example, when you think about what type of quality you need to actually safely feed your electrochemical system, and there are minimum concentrations. For example, the maximum concentration of magnesium plus sodium chloride should be 10 milligrams per kilogram of sodium chloride. Iron, there is also a minimum concentration of sodium chloride in the total dissolved solids, and of course there is a combined the total concentration of calcium and magnesium cannot be bigger than 100 milligrams compared to kilograms of sodium chloride. So if you can, we were looking into these 4 parameters to see if the current nanofiltration membranes would be able to provide the necessary quality for the electrochlorination. So the seawater and brine contain many other constituents based in besides in sodium chloride, thus require pretreatment to meet the feed. This was a work done by one of our students together, which was in an internship period in the Brazilian company in Cajassi, and she was using let me see, I think I have in the next slide. Oh no. So again, she was using, the idea was using nanofiltration as a treatment step. Okay, because there is a monovalent to divalent ions rejection, the divalent ions rejection is much higher in these systems. What did she do? She was actually exploring 3 possibilities. She was actually exploring 3 possibilities. All of them, it was a model. So she modeled 3 different possibilities, where she would get the RO brine, and the first possibility she would use a single pass nanofiltration, and then by selecting different membranes, we would see, okay, what kind of permeate we can generate, and we were using expected flows of the brine. We also know the expected composition of the brine because the partner, the company partner, gave the compositions and the flows to us. So we were using like close to reality values of concentration and volume to be able to simulate. The second option was actually to have a ionic exchange nanofiltration system to use the ionic exchange, especially for the removal of the calcium and magnesium. And the third option tested was actually a two-pass or two-step nanofiltration, where your permeate from the second step will be directed to the electrochlorination system. The permeate of the first step feeds the second step. The two brines, they could be used for energy recovery, but also we generate your final concentrate. Yeah. So which kind of results did we get? So if you think about the single pass, you should see the red line as the requirements that are needed to say, okay, this feed is good for the electrochlorination, is not good. So we need to have to reach this quality to be able to use the feed. So you can see that in single step, the sodium chloride to TDS concentration is not really reaching the necessary concentration. However, yeah, also not very far from the amount of iron based on sodium chloride content is quite good. So there is a quite good removal of iron based on the maximum that we can have, which is 10 milligrams per kilogram of sodium chloride. But the one which is critical is actually the sum of calcium magnesium concentration versus the total concentration of sodium chloride, which needs to be somewhere in 10, I would say, at 10 milligrams per kilogram. But what we get is in some cases close to 1.2 grams, close to 1 gram. Even if you do different types of recovery. So the one pass really did not presented itself as a good idea in this, or we could even say, okay, the sodium chloride to total solids concentration is not a big problem. So you decrease a little bit your total concentration, but the total volume of the plant is more than enough to have lower ranges here and still have the production demand that the plant needs. But this is critical. This is very critical because this will decrease drastically the lifetime of the electrochlorination system. And when you think about the single pass with an ionic exchange column, well, it's better. It's better. You can see, for example, here the critical parameter concentration calcium magnesium versus sodium chloride. We could get quite good values with 60% seawater feed mixture, but it requires seed mixture, and also it will add the ionic exchange. But it's possible as long as you have a bypass of seed mixture. And then lastly, when you think about the double pass, so nanofiltration first step, followed by nanofiltration second step, you can see that in this case, we actually are not that bad. So if you can see, for example, with the seawater in feed mixture, you can. Well, in the first step, we were far below. This is the first step, the one pass. But if you have a second pass, you can see that we can reach concentrations lower in the total amount of calcium magnesium per sodium chloride than it is required for DC. So in that case, after the first step, you have the same, of course, that we have already seen. But after the second step, when you use the feed of the first step, the permeate as a feed for the second, you can reach the calcium magnesium concentration. That is also quite okay for the sodium chloride TDS, even though we are still not really where we would like to be, which is above the 99%. However, as I said, this is not a very critical problem for us, not in this case, because just to give you an idea, we made some also big mass balance in the case of this plant in Fortaleza, in Ceará, and we actually need only 10% of the total brine volume to produce all the disinfectants that the plant would use. And so it is, we can compensate this again with using more brine volume. So the double plus increase the permeate quality after the second, and almost all EC feed requirements were reached after the second pass. It's important to say that in this system we did not, in this modeling, we did not check for bromine, for example, for all the type of contaminants, because basically it was the main requirements we get for this system was from a company partner in the Netherlands, they have, which gave us these parameters. But it's important to check also these other, certainly these other compounds, sulfate especially and bromine especially. Okay, some take-home messages. We reached now the end. So desalination is a plausible and well-established option to diversify our water matrix. If you have to move out, as we discussed in the first part, if you want to move out a little bit from this river groundwater matrix that you have, thermal desalination are big capacity system and competitive at low thermal energy costs. The seawater reverse osmosis now holds the big market share, so it's the most used technology in percentage, not in volume. We also saw this in the first one, because the thermal systems are still treating much higher, much bigger volumes. Different possibilities for brine management, however, mostly at low TRL, so still in scientific stage, in the bench scale or pilot scale stage. And brine discharge is a concern, and the legislation which imposes its management is for sure necessary. Yeah. Well, I would like to thank, of course, to many different colleagues that helped on this presentation: Esther, Marico Carneiro, Conrado Somariva, the platform of Almeria, where I also did a course in 2010 about the use of solar energy desalination systems. Colleagues from Cagesi, sorry for the people here, it's Cagesi, Silvano Porto, Holland, and also, of course, thanks to colleagues from CEB that have invited me for this talk, Jordi, Yovina, Martin, that has been also doing the role of a technical guy here, Sebastian behind the screens, and many others. So thank you very much. And now we can have some minutes for questions, if there are any questions, or for some discussions. If there are some discussions, let me know. So are you there, Sebastian?
Yes, I'm there. Just leaving space for the students in case there are any questions.
Yeah, we still have some half an hour, so it was a little bit faster than I predicted, but that means that we also have some time to discussions if there are any questions. If not, then what I suggest as well, again, Sebastian, I will discuss here with, maybe I go a little bit more like this, so you can see me like this. So what I suggest is that that I will discuss with Jordi and Martin, and I will also discuss with Uchi about how can we make the material available for the students, especially the papers and the presentations. And then later on, you guys can communicate them. But in the presentations, as you can see here in this slide, I also have my email there. So students, yourself, you can feel free to contact me if there are any specific questions. Okay.
I can ask a question.
Yeah, please.
The the schematic of the plant you just showed. That was in South Africa, I think I saw.
Which one?
Where you dispose the brine in the sea.
Oh, no, in Brazil. In Brazil.
That was in Brazil. Okay.
Yeah.
And because how do you, so you need to also have some information on the sea flow, I guess, to prevent
Yeah.
the brine being taken up again in your feed
Yeah.
flow.
Yeah, normally these studies are done not only for the flow method, but also for a general idea of in which position and which depth you should dispose of. But this has to be carefully done together with some marine biologists, with some shore management type of colleagues, so more the water management guys. Not really us, we are really in the technology part. On how to build the plant, on how to operate the plant, but this type of studies are really done by the ecology or the marine environment specialists. But yes, it has to be done for sure. I don't have the specific details about on how they do it, but it has to.
Yeah, and also the environmental impact, I guess.
Yeah. Yeah. So there are, of course, legislations and regulations on the amount of have to do based on oceanic flows and deep and depth. And this is clearly established. So that's why we can calculate this discharge. But in my view, and from what we have been also discussing in the brine management part, yeah, we shouldn't, we can and we should be a little bit more strict on this point. Yeah. And if you see like the paper represented, yeah, some experiences that other authors are reporting in Israel, Saudi Arabia of this big desalination plants, you do see already some where they can actually give perspectives of many years of operation, because these plants are from the 80s, 90s. And the thing is, with these environmental impacts, you normally need some kind of time window to be able to expose this impact. In these studies, you can clearly see that there are impacts in the marine environment, on fish migration, and other aspects. That's why we need to be more rigorous on this aspect. It has to be also considered that well, in the 80s, 90s, when these plants they started, the volume, the total volume they had. And therefore, the amount of brine that existed that was discharged was not that big. So we had some plants in Saudi Arabia, we had some plants in the Mediterranean region, but it's becoming for years already, maybe for a decade already, is becoming a more and more used technology, and therefore the amount of brine increases, the amount of produced water increases, the amount of brine increases, and the impact also increases. So you have to look again and evaluate again on your parameters.
Yeah. Thanks.
Yeah. Okay. Well, thank you very much. So if there are no questions, I say goodbye to you all. Unfortunately, I heard from Martin just now in the break that there will be a summer course, which probably some of you guys will come to the Netherlands, right, Martin, in July, maybe. But and I would love to say hello to you personally, but I will not be around. I'll be in Brazil for the month of July in a visiting professor position. But well, I'm sure it will be very well received by my colleagues from CEW, and luckily you will have a great time. So also hello to you, Sebastian. Thank you for organizing from your side, and hopefully we see each other some moments soon. Yeah.
Thank you very much. Yes, and see you sometime.
Thank you. Bye bye. Thank you.
All right.
Thank you.
Have a nice day, all.